Hey, everybody. Thanks for coming to my talk. I see some familiar faces out here. It means the world to me. And this is also a little bit of an experimental format for me. So what we're going to have is 2 presentations and running code. And so we're also going to be talking about the mental load of running code and having lots of processes running. So we're going to try it on stage and see if I break down. We'll see. My name's Dawn Wages, she, her pronouns. I live in Philadelphia with my wife and 2 dogs, and I've been in the Python community for about a decade, but I am really, really thrilled to be here. It's my 2nd time on the PyCon US stage. The context of this presentation is why is it so hard to build a software environment, and specifically a Python environment, and then leaning into some of the vulnerabilities of having human-first component of code. And if you've seen me talk about some of these topics across the year, this is a running theme. It may look similar to some previous presentations I have, and if you get a chance to catch me at PyCon Italia, it'll be a similar context as well. In a moment of vulnerability, I came into the Python ecosystem as a Django developer and then moved into product maybe about 4-ish years ago. And one of the first and silliest things that I said to my team member, Luciana Budd, was, "Are Python environments that hard?" Yeah, yep. And the raucous laughter is absolutely warranted because I came from, and I think there's 3 reasons why I said that. One, I came from a place where if I failed, it was my fault. It wasn't the code, it wasn't the documentation, it wasn't the package that I was trying to install, it was me, and I internalized that failure. Second, I always thought that coding was a team sport. I came in through Django Girls, shout out Django Girls 2015, and a lot of the times that I was building code, I had competent developers around me, and I had people always to ask questions with. And so when I had trouble, there was someone else that I could offload some of that mental load to. And then third, when I came into programming, maybe in the 2015s, I think it was probably a little bit before that as well, it was a rapid investment in developer experience. So it wasn't just getting the code live and up and doing the thing that you needed to do, but it was about the enjoyability of building the code. So I didn't also realize how much work was underneath the abstraction to build some of these environments that I've been using, and using not always seamlessly, but without complaint. So in this talk, we're going to have a bit of a game. Every time you see broken code on screen, I want to hack our brains and cheer. So instead of being sad or having a groan, I was thinking about making empathy, but I want us all to do a bit of like a round of applause or a cheer or woot. Can I get a practice round? Oh, wow. Oh my God, that feels really good. This is my first time doing this one. I am so glad I picked a raucous applause. We're going to do that about 5 times through this presentation. Thank you so much. So as I mentioned, Dawn Wages, I lead community and developer relations for Anaconda, and I also host a podcast with Luciana Budd, who's just so lovely. Some of you have had the pleasure of getting to know her. And we've been on hiatus, but it's coming back this summer. So if you are familiar with Sad Python Girls Club podcast, you can find us on where all podcasts are, watch our old episodes, and new ones will be dropping this summer. I also talk about local first AI ML. It's something that I'm kind of growing into. I mentioned I started in Django, so if you want to learn with me, follow me on all the socials. So it's in the title, but what is spoon theory? So it was coined by Christine Miserando, and it's originally about chronic illness, but it has a really surprising and resonant alignment with the cognitive workload. And so one of the insights is it's not just about energy is finite, but there's also different task costs, and that you don't always get to choose what that task cost is and when you have to expend that energy. The costs are not visible, and you can't always choose how to spend it. So as you're managing with limited energy, environment setups is almost entirely miscategorized as this free overhead, When a developer ends up sitting down and sees these dependency conflicts, sometimes it's an ambiguous path. Maybe it's a broken virtual environment or unclear Conda or pip interoperability. They're spinning spoons that was supposed to be already done in many cases or expected to be done. So that cognitive cost isn't just about the technical challenge, but it's an interruption in attention and intention. So you're a developer, you start your day, and not all of us are lucky to start our days with a full spoon. You expend that cognitive effort to write down your to-do list. Hopefully these next few slides do not make you too anxious because they hit home. But you write down your to-dos for that day. And inevitably, you forget in that first pass to talk about the human things that you need to get done. I gotta walk my dog. I gotta make sure I call my maintenance man. Or maintenance person, but mine's a man. Those tasks are ultimately written, and then sometimes you forget that you need to expand or adapt them. And you do some of those things. You fill your cup, you sit down for breakfast, you stretch before you sit. You're doing the work, you're investing in yourself. You go through your stand-ups, you start your day, maybe you knock out an issue, and then lift gets even heavier. You try to remind yourself to continue to take care of yourself through the day. And your day just gets even more hectic. Without a reprieve, you just make it through. But even what you have on paper, this isn't all of it. Some of the things may require feedback or context switching. You may need to stop, change gears, or restart. More context switching. And then maybe you'll ask for help from another team, but whatever that interface is, you're doing it on someone else's terms, so maybe you're dealing with time zones or busy schedules. It's not easy. And by that 2 p.m. slump, you're almost on empty. So let's do our first demo. All right. Let's do a clear. You see the last of what I did. Oops. There you go, actually. That's great. All right. Right. This one failed. Now do another one. Woo! Thank you. So why did it fail? Well, this one first was about an import error. So this one specifically, and if you want to go through any of these demos, if you find the link is on the bottom of this slide, so you can follow through on any of these, that PyCon Spoons 26. But this one was specifically because QP is a NumPy compatible array library for CUDA GPUs, and it does not support Apple Silicon the way that I have it in this demo. And if I want to switch it out for MLX or Torch or JAX, none of those are drop-in replacements, so migration requires auditing every QP call, perhaps. All right, let's get back. So why do environments fail? And then we're going to go through why do we fail. And there's 3 modes for a memory model, switching tax, and masking tax. But for why environments fail, we have 2 modes, abstraction and process is what I love to kind of dig into. So this is the abstraction layer that I like to bring up on my slides a lot. This should look familiar for people who are interested in a perfect representation of what that abstraction process or abstraction layer could look like. And this is a perfect representation of what your personal process could look like. So going down through that abstraction, you have your application or user intent, your runtime, your package dependency. You're isolating your environments. You have the processes or OS interface, hardware abstraction, and then that physical firmware. And then your process, this may look very familiar, but you're planning, designing, building, testing, and hopefully shipping. But abstraction can be messy. Sometimes extensions bypass runtime. Sometimes layers that are substitutes for each other. And then sometimes novel hardware are used for different purposes, or you have developer-focused hardware, which has its own problems in and of itself. And that process is not easy either. This is more of like what my real process looks like. I'm turning my planning up on its head. I have false starts, redesigns, and in imperfect ways, I'm in ecosystem considerations and releases. So let's talk about why environments fail, but before that, let's go to our next demo. All right. Okay, it failed. That is so nice. I think I might want to record that, bottle it up. That's really lovely. Why did this one fail? Let's go back. All right. We talked about some of the hardcore assumptions and realities. Why did this one fail? Well, libgomp.so.1 is not there. And this one's specifically a naming error. So there's a naming mismatch. The problem not found at runtime, specifically, no amount of searching can fix this mismatch. It was done, and I have more notes on this if you want to dig deeper into this. But this one, Mac OS, which is what I'm using, doesn't have the same name as what you would use on a Windows system, and so it routes through a different tool, through LLVM. In this particular one, this one's actually really interesting because the package installed, pip reported a success, but the failure only surfaced itself at import time because of the OS dynamic linker. So let's keep going. So the top layer, this is the user intent. This is exactly what the developer intended to do. This is the correct layer. So for example, you're writing an algorithm that is built on a particular hardware or runtime, and it's because of the operation changes or process flows, it's not the same runtime that you end up running, so running the operation in. We also have the runtime and interpreter layer. This is a translation layer between Python syntax. So CPython, PyPy, Python 3.13, each makes different promises about the guild, the garbage collection, or what C extensions can safely assume. And then we have the Python interpreter, which is also a bit of a can of worms. When you run your Python file, when you run your Python through CPython, it does several things in sequence. It will start with your Python file and then abstracts into a syntax tree. It will run through the Python interpreter, turn into bytecode. And the lower level sequence of the instructions are stored in .pyc files, and then it executes in that bytecode on that Python virtual machine. And then it also can run, it never runs directly on that CPU because CPython then reads each bytecode instruction and executes that corresponding C for it. Next is package dependency. So package dependency is where you're introducing even more of that human social contract between library authors about what versions coexist or what the release cadence is. Some of it is implicit, some is documented, and some are written for hardware targets that are expected, and you may bring in some unexpected hardware targets that isn't yours. We also have environment isolation. So that is that boundary between the project's dependencies that are this project's dependencies versus that project's dependencies, versus like Conda, Vim, Docker. These are environment isolation tools, and they all attempt to draw a line that the OS doesn't naturally enforce. Process and interface, file descriptors, locale, signal handling, memory defaults. These are all mount points, and OS enforces constraints that the developer doesn't always know. And you may not know it until 2 a.m. when you're hacking away. All right, let's go back to our next demo. I think we're on 3. All right, almost, now it failed. Yay! All right, let's talk about why it failed. And really the goal of coming through some of the why it failed is to give you just examples on how taxing and detailed it is. This requires tens of thousands, if not hundreds of thousands of hours from developers across the world, really resolving some of these deep, complex issues. So when you are running into a problem, it's not always you, it's an ecosystem, and we're solving it together. And as I'm calling out some of these packages or tools or operating systems, and I know people in the room who are contributing to it, it's an ecosystem consideration, and I'm so thankful for the work that you've brought us here thus far, and being able to learn more about this in this presentation has gotten me even deeper into some of these considerations. Yeah, let's do a cheer for the OSS maintainers. Yeah. All right, so why did this one particularly fail? This one is about, so this one was, there's 4 things in this particular one. I'm gonna glide over it for the interest of time. But there's a path problem in your OS interface. Mac OS volumes is dynamic, while Linux mount presents very differently. There's also another one that's about sim linking, so the link of the simulated link is there. So when you check is exists, you get true, but when you check what the link actually is, you get false. And then there's another one that I did, a failure that was just ran, where there's partially written files, and because you've articulated your capacity, just the disk capacity decision earlier in the process, and you write too much to disk, you don't actually realize the error until later. All right. Yeah, and that's a little bit more on that. Cool. All right, we are on the, did we do hardware abstraction? Yeah, let's do hardware abstraction. Varied physical compute looks uniform from one angle versus another. This is a layer that pretends compute is equivalent, so maybe the CUDA interoperability, MPS, or CPU are all not the same, and they have different support types, different precision guarantees, and there's different failure modes at the same API surface. And last but not least is the physical firmware. So this is a layer that really doesn't negotiate. You're not very flexible in this one, but it doesn't negotiate unless it does, because what if you're just gonna put it on different device? And then you got more issues. So no amount of correct Python resolves the fact of the physical world. So now we're building into process. That perfect process gets messy. I'll go really quickly kind of through this one because I'm sure we can all internalize it a bit more. But if you want to go in the hallway track and get my full notes on this, I really have been cycling on some of these concepts a lot more because it's been really interesting for me to dig into some of these abstraction and process-oriented considerations. But the ideation phase decides what exists today based on prototype of what's on your laptop, but your plan phase will estimate perhaps work. Tests are written against the environment that currently exists, not the one that will exist, and you have to continue to update that. Your release flow is aligning with the rest of the ecosystem perhaps, and your build pipeline and your ecosystem cadence will release on coordinated schedules, but are they really that coordinated, and how can the human element get in the way of that? So why do we fail? So we went really deep into a lot of the technology. We have 2 more failing demos that we're going to cheer for, but the rest of this is about what provides stress for us and why do we sometimes have become the bottleneck. So I want to talk about the memory model. This one's interesting specifically for the to pull away from it is your cognitive tasks have limits. That is one of the central premises of this presentation. And you have this supervisory system that allocates attention. There's also 3 other modes that makes us feel like our brain has this neuroplasticity, has this elasticity, and if you just push harder, it will go faster, longer, stronger, and that's not always the case and can lead to burnout and not good feels. All right. We also have the switching task. So every time an environment breaks, it forces a task switch. There's a research study, and all of the sources are cited at the end of the presentation if you want to read into some of this research. But it triggers a chain of diagnostic tasks that extend the switch duration. 23 minutes was this researched and re-researched number, and that encapsulates the entire time of getting distracted, finding a new task, realizing you're distracted, and then coming back. That is like the average duration, which I thought was really funny. And this generates stress that persists until you resume the work, and that is also a kind of a research study as well. There is a mental overload for unfinished tasks, and when given the opportunity, people will innately just go back to their original tasks. Let's go to one of the last two demos. I think we're on 4, right? Yeah. Yes, and this was designed. Yeah, sure, almost breaking. And then real break, yeah, woo. Okay, why does this one break? This one is a platform mismatch. We have a misconfiguration. So Docker, this one's all full of Docker fails. You have a platform mismatch, unable to allocate memory in the second example. There's also Docker does not actually try to inherit the shell environment that is necessary for this example. These all kind of dummy toy examples that mimic real things. It is actually running on my machine, so that's good, but it's all dummy toy examples that you can play with. And the last one is times those are hard. Okay, I'm almost done to the last part of the presentation. So one of the last mental loads and why we fail is miscategorization. So I mentioned it at the very beginning, and it's a kind of a great through line on work is not free. We assume that there's going to be this low setup cost sometimes. If it worked on my machine and I'm not documenting to support other workflows, it is easily able to be a discounted tax on that invisible load. Yeah, and then what is the ecosystem doing about it? So I encourage you all to go deeper on some of these things. There's absolutely PEPs that if you want to wonk out on PEPs, I think they're really, really cool, and I've been getting into them a little bit more in the last 3 or 4 years. So PEP 751 was accepted in 2025, which standardized a lock file format for pip, which is called pylock.toml. We have PEP 723, which was in 2023, which introduced inline script metadata. Docker and OCI containers address environment reproducibility by capturing the entire OS layer. So the proposal, it's not just the Python layer, but the problem that they don't solve is that there's one demonstrated that the platform architecture could be a mismatch. And then the last one is multi-arch builds for like Docker build X, for example. This addresses this, but it requires this explicit effort in the CI infrastructure. All right, last demo. I can't believe I timed this, okay. What in the hell? All right, almost. It's building, and some pass, and then it'd be so funny if it just all passed. No, they're designed to fail. They're designed to fail. Oh, there, yay! All right. And let's go back to why this last one failed. Oh yeah, we were talking about emulations and the Docker fail, okay? And then why did this one fail? So this one was all about dependency failures. We had a dependency conflict. We picked the wrong interpreter. We had this conda and pip cobbler in one of the examples. There's 5 in this one. We also have a broken editable install in this presentation. And then the last bit is there is an architecture mismatch again. All right, so last bit of the presentation. I want you to have, and this is a theme that I have through a lot of the presentations I have, you may have seen this slide before, is I want you to have the sustainable autonomy, the ability to own and understand your stack, and I want you to have this deliberate ownership. Getting curious about the ecosystem that supports you, the hundreds of thousands of hours that is invested in this, it gives a language of sovereignty and ownership and excitement in your ecosystem, and you're also able to offload, if you're like me, some of the ownership of failing infrastructure, failing environments. Thank you so much.